We're going to talk about fluid dynamics now. We've been talking about statics, things floating, or pressure where everything's staying the same, but now we're going to talk about liquids in motion. And there are two main ideas we need to think about here. One is when you have fluid going from a small size hose to, say, a bigger one, what we need to say is that as long as we're not compressing the fluid, that whatever volume is flowing needs to stay the same. The volume needs to be the same. In other words, if we have 5 gallons per minute coming in, it's not like we can store that 5 gallons somewhere in the system. We need to have 5 gallons per minute coming out. And so what that means is that if we have a volume like this kind of coming in, that maybe shows up as a volume like this coming out, right? So this is a bigger cross-sectional area. So this is a bigger area, A2, and this is a smaller area, A1. And so what we can say for that volume is that the volume would be area A1 times L1, and that's going to have to be equal to A2 times L2, right? So if A2 is a lot bigger, then L2 is going to be much smaller. Now, we don't often measure the lengths, but instead of a length, if everything's moving in this region at basically constant speed and over here in a constant speed, we can write this a distance in terms of the flow, V, of the water that happens over a time. So it would be like, how long does it take for it to go this length, which would be V times time, and then it would be that same time to go that distance over here. So we could also have L2 would be V2 times its time, right? So that we get the same amount of volume. So if we plug this in, this gives us that A1 V1 is equal to A2 V2, and this is what we call the continuity equation. It's a fancy name for saying what goes in must come out. And so if we have and this is not a surprise, that this means that we have a fairly high speed here compared to a much smaller speed here. And you know about this. If you take a garden hose and you cover the end of it, you get water spurting out at a much higher speed, which of course means it can go further before it hits the ground. Okay, so that's the first piece that we need, and this allows us to do some calculations, but this is fairly important. The volume stays the same. The next thing we can do is we can analyze what's happening by looking at the energy pieces, if we don't have to worry about friction. So this is the no friction. So for this means no viscosity, basically. This is a water smooth liquid. It's not molasses, okay? So it's like water, but water even has some, water has some stickiness as well. But basically there's no friction, which means a laminar flow. Everything flows really nicely. It's not a bad approximation for water, and we can use it at least to start with. And so in this case, what we can look at is we can say the work done plus the work that's done can go into done on a fluid, like by the pressure behind the fluid, something pushing it along. The work done plus the kinetic energy and the potential energy must be basically a constant. So this is basically conservation of energy. In other words, the work goes into either kinetic energy or potential energy. So those are the places that we can say this is our energy conservation, because we've got no friction, so we don't have any thermal energy. So work, if you remember, is force. I'm just going to do this kind of as a unit setup almost. Force times a displacement. Kinetic energy is 1/2 mv squared, and gravitational potential energy is mgh, right? Equals a constant. But with liquids, we tend to like to work in terms of densities, right? Because we don't know how much mass we have at any one time. So if we divide everything by volume, so I'm going to try to use this capital V to separate it from the speed here. Still dividing by volume, still equals a constant, right? So this now gives me something as 1/2 the density times the speed squared plus the density times GH equals a constant. And then if we look at this, this is force times distance over a volume. Well, a volume, remember, we can write as an area times a distance. The distances can cancel. Force over area gives me a pressure. So this actually wraps into, if our speed is 0, this is another way of getting our pressure at a depth. It says at the top, if we compare it with the top and the bottom, this term is constant. And so what this means is, for example, if we look back over here, we say, hey, this is the same height, call that height equals 0. So that's the same. Then we could say, just looking, pressure 1 plus 1/2 rho V1 squared must be equal to pressure in 2 right here plus 1/2 rho V2 squared. We know that this V is bigger. This is bigger, right, from this continuity equation here. And so that means that if this is bigger, this must be smaller. So the pressure here, P2, is bigger than the pressure over here, P1, which is not a surprise really, because if we're going from a high speed to a low speed fluid, right, our speed was big and it's low down here, there must be a net force in this direction to cause an acceleration to slow down. So it makes sense that the pressure is higher over here. In other words, we got a higher pressure compared to this. And so this is a way we can sort of analyze pressure changes depending on the speed of the air and also at different heights, which when V is equal to 0, that gets us back to the expression that we've already used.